So the results in the previous slides that we found were the analytical solutions. And now we want to approach this problem using a numerical method or a numerical model. So let's remember that this was our analytical or exact solution. To be able to have an alternative numerical solution to this parachutist problem, we will use some calculus knowledge. For example, the dv over dt, which is the derivative, can be defined as a limit delta v divided by delta t. And because delta t is finite, we can assume that dv over dt is nearly equivalent to, approximately equivalent to delta v over delta t. So we can simply use this approach, and then we can say that dv over dt, which is approximately delta v over delta t, which means v in two different times, consecutive times, t e plus 1, the difference of the velocities between ti and ti plus 1 is delta v, and delta t is ti plus 1 minus ti. So we can graphically show this. For example, this was our curve, analytical curve, and here for the ti we have a vti value, and for ti plus 1 we have vti plus 1 value. This kind of, for example, the time is 2 and time is 4 and delta t is 2, for example. So this simply dividing by delta v to delta t, we will have an approximate slope, which is a linear slope because this is a linear formulation. We will have an approximation of this curve by this linear line, let's say. The true slope is this actually, because it's tangential to the beginning, but the approximate slope is this. I mean, there is a large difference, it seems, but it still makes a good assumption. And if we reduce the delta t, so we have a smaller difference between ti and ti plus 1, then we can have a better approximation of the slope and better division of these to be able to approximate this in a better way. So this is kind of a numerical solution. What is the advantage of this? We don't need to know about the analytical formulation and just use this the difference between v's and t's to be able to have the velocity. And let's try to use this and solve this falling parachutist problem using this numerical model. So if we continue on developing the numerical model for the parachutist problem, if we remember from the previous slide, our dv over dt, we said that this is approximately delta v over delta t, which is vt plus ti plus 1 minus vti divided by ti plus 1 minus ti. So here we substitute this approximation dv over dt into our parachutist problem formulation. In other words, dv over dt equals g minus c over m v. This was our initial analytical equation, and we actually integrated this to find the analytical solution or analytical equation to find the v. But now let's assume that we don't know how to differentiate this. In that scenario, we just simply use this numerical approach, and we don't really take any integration. If we put it here, vti plus 1 minus vti divided by ti plus 1 minus ti is equivalent to g minus c over m v. This v is the initial, or the velocity at ti. And if we isolate vti, this one, because we don't know that, but we assume that we know the initial velocity. If we start from 0, we know the velocity at 0 because it's 0. Then we find this, then we can easily increase the time and find the other values. So we isolate vti as follows. Here, let's put this vti to the right side. Vti plus this term on the right side still exists, vti, and we multiply this by the subtraction of ti plus 1 and ti to isolate vti. Okay, now we have a formulation for vti plus 1, as you can see here, and this is simply a good formulation to be able to find all the velocity values. And if we generalize this, you can see that this is the new value equals to old value plus a term here which is called the slope actually times the step size. In general, step size means that the difference between the first and second, or the next and previous step. So this generalized equation below is called the Euler's method. This is a widely known numerical approach to this kind of iterative solutions to find all the values at each time, for example. And we can use this Euler's methods in any other problem that we want to formulate in a similar manner. But you can see that from this example, we can simply formulate this. And now let's use this equation to find the v values at each t numerically. In the next slide, we can do that.